Okay, so so this is the third line is known as our design curve. This third line, the lowest one. Okay, this line, this is our design curve. Okay, and in this design curve, the strength you will get this value divided by partial safety factor, and if you do it, you will get the value 0.45 FCK. Actual value is 0.446, but actual value is 0.446, but in 2 digits it will be 0.45 FCK. Okay, so now what does this line means? Okay, up to this point, you will get parabolic portion. Okay, so at this point means at this point you will get the maximum strength, and then if strain is occurring means you are increasing the load, and strain is occurring. Okay, strain is occurring, but beyond this point if you increase the load, what will happen? This is our ultimate strain, or beyond this point your structure will fail. So ultimate strain is 0.0035. Okay, so this is the stress strain curve for concrete. All of you must remember this curve, because in exam you might find a question on this curve. Okay, stress strain curve for concrete. Okay, so let us see the next one, which is our stress strain curve for concrete steel. Okay, so we have two grades of concrete. One is our mild steel, another one is our HYSD bars. Okay, so this is the stress strain curve for mild steel. Okay, and the curve will look like this. This is the first line will indicate the characteristic curve, but for getting the design curve, what we have to do, we have to design the Fy value by partial safety factor 1.15, and you will get 0.87 Fy. Okay, so this line means you can see this axis represents stress, this represents strain. Okay, so you are increasing the load this much. Say you can, for mild steel means Fe 250. When 250 means 250 Newton per millimeter square area. So whenever you are putting 250 Newton per millimeter square load, so at this point you will get a strain of this much. Okay, so this value you can find out by this formula. Epsilon y means stress at this point, strain at this point will be 0.87 Fy, which is our characteristic strength, divided by Young's modulus for steel. And this value is, for steel we will take it as a constant value. The value is 2 into 10 to the power 5 megapascal. Megapascal is, it is nothing but Newton per millimeter square. Okay, so ES value will be 2 into 10 to the power 5, and at this point your strain will be 0.87 Fy divided by ES. Okay, and so this is the characteristic, this is the stress strain behavior for our mild steel. Okay, so next let us see for HYSD bars. Okay, so in HYSD bars your curve will be a little bit different. Okay, this straight line portion, that means up to this point, this is our elastic region. Okay, elastic region, you can see a straight line is there. That means your stress is increasing as well as your strain is increasing. Okay, so up to this point, that means up to the elastic region, you can see the maximum strain is how much? 0.002. Okay, here also you can see here 0.002 means up to this point your elastic region exists. Okay, elastic region means your stress is directly proportional to strain. Okay, so now beyond this point you can see your parabolic portion starts. Okay, parabolic portion starts, and from this point to this point, this is our plastic region. Okay, plastic region means your permanent deformation will start. But that doesn't mean that your concrete will fail, your steel will fail. Okay, because you know that steel is a ductile material, so your deformation, it can resist very much deformation. Okay, so at this point it will reach the maximum value. That means if you are using Fe 500, because HYSD bars can be of two types, one is your 415, another one is Fe 500. So say we are using Fe 500, so at this point you will get the maximum amount of stress. Okay, so and beyond this point, if you remove the load also, you can see that some amount of strain is occurring. Some amount of strain is occurring. Okay, so now at this point, how to find out means at this point this is our maximum stress. Okay, and which is our characteristic curve. For getting the design curve, you know that we have to divide the value by partial safety factor, that is our Fy divided by 1.15, which is our 0.87 Fy. Okay, so corresponding to this point, if you have to find out the strain, okay, means at this point, so how to find out the strain? Up to this point, the value was, means up to the elastic region, our value was 0.002. And for this portion, we have a formula 0.87 Fy divided by Es. So the total strain at this point will be 0.002 plus 0.87 Fy by Es. You can see this. Okay. So at this point, the strain will be 0.002 plus 0.87 Fy by Es. You have to add this whole value because we need the deformation, we need the strain at this point. So you have to find out this whole value. And this value will be 0.002 plus 0.87 Fy by Es. Okay. Okay, so now let us see the PDF. Okay, wait. Yeah. Now I have a PDF with me, so I'll show you. Limit state concept, everything, the theory portion, whatever I have explained, this everything is written in this PDF. Okay. As soon as this portion will be over, I will share the PDF. Okay, this is our limit state of collapse. This is our limit state of serviceability. Then we can compare what is the limitation of working stress method and what is the advantage of limit state method. Everything you can see here in this PDF. Okay, so these things already discussed, so no, I'm not going through these things. So design strength, this is the thing we have got in IS 456. Okay, partial safety. Remember these two values. Okay, all of you please remember these two values. Your partial safety factor for concrete is 1.5 and partial safety factor for steel it is 1.15. Okay, so now can you tell me one thing? Do you have this question in your mind? Why the value of partial safety factor for concrete is more and why the value of partial safety factor for steel is less? Anyone? Anyone? Do you have any idea? Do you have any idea, or do you can use your common sense also? Why it should be less, why it is more?
Sure,
Yes.
because the changes of vibration in the properties of steel are small.
No, 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 no.
System here.
Safety factor means for safety factor, you know what is safety? Yes. For safety, we are considering a higher value for concrete, and for steel, we are considering a less value. That means this value is 1.15, this is 1.5. So, can you use your common sense, or can you think that why it is more, why it is less? For concrete, why it is more, and for steel, why it is less? Anyone? Or can you guess the answer? Anyone can? Yeah, I think this Hoketo has guessed the answer, but that was not correct. So, anyone have any other answer? Anyone? Shiroda? Okay, so steel more elastic than concrete. Steel is bit Better. No. More elastic. Steel is a better quality. Okay, how better quality? How it is a better quality? Shiroda? Because it is strong in tension as well as compression, that's why. Yes. No, no, no. Okay, wait. Okay, so I will tell you what is the reason behind it. The same question you can get in Viva also, because this semester you have to appear in a mock test. Okay, at the end of the semester, you have to appear a mock test. That means one expert will come from outside and he will ask some practical questions. Okay, so the reason behind it, it is that our steel is manufactured in industry. That means it is manufactured mechanically by using some machine, okay, or some advanced techniques. So the chances of default or chances of this error while producing this steel, it is very less. But in case of concrete, since it is we are making it manually at the site, so there is a high chances of error. Okay. Okay, so since we are making steel in industry, that means we are using some mechanical machines to manufacture the steel. So the quality of steel is very much better than the quality of our concrete. Since we are making concrete manually, so the chances of defect is very much higher than our steel. So that's why the safety factor for concrete is we are assuming it is more, because the chances of error is more in case of concrete. But since the chances of error in the quality of steel it is less, so we are assuming we are taking a lesser value for safety factor. Okay, so this is the reason. Say here it is also written here, a higher value of partial safety factor for concrete has been adopted because there are greater chances of variation of strength of concrete due to improper compaction. The reason is written here. Okay, you can read this one. The reason is written. The chances of variation in properties of steel are small because it is fabricated or it is manufactured in factories where good workmanship and better quality control can be achieved. Okay, so therefore a lower value of 1.15 has been adopted. Okay, you can read this PDF. Okay, so next, these things already discussed, this one is discussed. Okay, so our main part, let us come to the main part of the syllabus. Okay, so which is our, we will start first by limit state of collapse in flexure. Okay, so these things are given in IS 456. Okay, we go to clause number 38.1. Go to clause number 38.1. These are the assumptions. You read the assumptions first, because these assumptions we need to use throughout the syllabus. These assumptions we have to use throughout the semester. Okay, so the first assumption is plane section normal to the axis remains plane before and after bending. Okay, so can you tell me the meaning of this line? Anyone? What is the meaning of this plane section plane section remains plane before and after bending. Can you tell me the meaning of this line? Anyone? Can anyone tell me what is the meaning of this line? First assumption. Can anyone tell me the meaning of first assumption? Okay, so I will tell you now, okay? Okay, say this is our beam, okay? And say this is a one axis, okay? So I am considering this portion. Stress is uniform throughout the beam. No, it is not the section. Okay, so see, say this is our beam and this is the condition before putting any load, okay? So now you see this portion. You see this portion. At this portion, this is the axis normal to the beam, is it? This portion, this portion. Okay, so now this section, so now say you are putting load now. So now you will start putting load now. Okay, so now you have started to put some load. Okay, so these are the loads you have put now. You have put now. And as a result of that, your beam will bend like this. Is it? Okay, as a result of that, your beam will be bent like this. Okay, so now what is the meaning of that? The meaning is, if you are considering this section, that means at this portion, say here. So now your axis, previously your axis was this one. Previously your axis of the beam is this one. Before putting the load, this is the axis and this is the section perpendicular to the axis. I am considering this section, okay? You can consider here, anywhere. I am just for explaining, I am considering this section. Okay, so now after this bending, your axis will also change. Your axis now, it will be like this. Your axis of the beam will be like this. Is it? Your axis will also bend accordingly. So now, what is the meaning of the assumption? Say if you are considering this section before the bending, so after the bending, your section will become like this. So at this particular section, you can see the section perpendicular to the axis before bending and the section perpendicular to the axis after the bending. Both are same. This one and this one, both are same. Okay, so do you understand this now? So previously, before putting any load, that means before bending, say this is our beam, this is the axis of the beam. Okay, this is our axis, this is our axis. Okay, this is our axis, and I have considered one section perpendicular to the axis. Okay, so now you started to put load. So as a result of that, your beam will bend like this. So your axis will also become bend like this. Okay, so if you consider the previous section, whatever we have considered before the bending, say this is the section. So according to the assumption, this length, this length before the bending and this length after the bending, they will remain same. Okay, so all of you understood by this assumption what is the meaning of the assumption? All of you, do you understand what is the meaning of the assumption? Do you understand the meaning of the assumption? All of you? Again, okay. Okay, so this is our beam. Okay, so this is our beam before the bending. That means before putting any load, this is our beam. Okay, and this is our axis of the beam. Okay, and I have considered one portion. I have considered one portion normal to the axis. Okay, wait. I have considered one section normal to the axis. Okay, so this is the axis before the bending of the beam. Okay, this is the section, this is a small section of a beam before the bending of a beam, before the bending occurs. So now you start putting the load on the beam. So as a result of this load, what will happen? Your beam will bend like this. All of you know that. So your this axis, original axis, will also, it will be changed now. It will be like this. These lines are not straight exactly, so but I hope you understand. Okay, so your axis will also shift like this. So now if you see the section, this section, whatever section we have considered before, if you can see the same section here, this is the section, this one. Because of the bending only, it will shift like this. Okay, before the bending it was straight, but after the bending it has become like this. Okay, so now according to the assumption, this section and this section both will be same. Okay, according to the first assumption, before the bending this section and after the bending the same section will remain same. Okay, that means this length will be same. This length, if this is x, if this is your x, if this length is x before the bending, if this is x, so after the bending also this will be your x. Okay, so do you understand now, Sheila? Do you understand now? Okay, thank you. Okay, so now let us go to the next one. All of you see the IS code, okay? All of you see the IS code. I am explaining this in from PDF. The second assumption is the maximum strain in concrete at the outermost compression fiber is taken as 0.0035 in bending. Okay, that means I have shown you the graph here. Here, this is the maximum strain in concrete. Beyond this strain, that means beyond this deformation, what will happen? Your concrete will fail. So the maximum strain in concrete in bending is 0.0035. Okay, this is the meaning, 0.0035. All of you remember this value. All of you please remember this value. The maximum strain in concrete at the outermost compression fiber is 0.0035, but it is only in bending. Okay, it is in bending. This value is in for bending. That means when your beam is bending, that in that case the maximum strain that will occur in the concrete will be your 0.0035. Okay, so next, the relationship between the, you can read the PDF. Okay, you can read the PDF. You can read your IS code. You can read the IS code. Everything has been explained before. You go through the assumptions. Oh, wait, okay. So if you don't understand again anything, you can ask me. Just go through the go through your IS 456, and if you don't understand any assumption, then you ask me. Go through the assumptions, because these assumptions are very very important, because we have to use these assumptions every numerical. In every numerical, we have to use these assumptions. So all of you, please go through it. Please explain point number D. Yeah, the tensile strength of concrete is ignored. Just like the previous working stress method, the tensile strength of the concrete is ignored. That means the entire tensile stresses will be carried by our steel. Okay. Point number D. Point number D is the tensile strength of concrete is ignored, means the entire tensile stresses will be carried by our steel and none by concrete. Do you understand now? Okay, though? Okay, thank you. Okay, so I hope all of you have understood the assumptions. Is it? Explain point number C. Okay, okay, okay. Wait for 1 minute. Okay, let me give the attendance. Okay, no need to write down in the chat box. Okay, I can see your names and as well as enrollment numbers. Okay, so the stresses in the reinforcement are derived from representative stress strain curve for the type of steel used. Typical curves are given in figure 23. For design purposes, the partial safety factor gamma m equal to this one. Okay, so these are the figures which are given for steel. Okay, so for steel, I have shown you these images. Yeah, these images. Okay, So from these images you can find out the what they have said. You can find out the for design purpose the compressive strength of concrete is assumed that not this one. Yeah, this one. The stresses in reinforcement are taken as stress strain curve for the type of steel used. For design purpose, the partial, okay. That means this one. This is our characteristic curve, okay. That means without using our partial safety factor, you will get this curve. But for design purpose, according to IS code, we have to use our partial safety factor. So partial safety factor means if you use this partial safety factor, so Fy divided by 1.15 you have to use because we are considering for steel. So you will get 0.87 Fy. That means this is our design strength of steel. Okay, design strength of steel. Okay, so now at this point, that means at the elastic point, what will be the strain? Your strain will be given by this formula. Okay, 0.87 Fy divided by Es. Okay, and this is for, okay, so our meeting will be meeting will end within 5 minutes. Okay, but let us explain this one. For mild steel bar you will get the straight line. Your steel is this one, you will get this one. But if you are using HYSD bars, your graph will be like this. Okay, so up to this point you can see this line is straight. That means this portion is our elastic region. Okay, so at the elastic region your strain you will get as 0.002. But after elastic point, if you go beyond, that means you are continuously putting the load. So at this point, you will see that the stress has become the maximum value. Okay. Say if you are using Fe 500, the maximum stress it can carry 500 only. So at this point, you have seen that your stress has been reached. The maximum value of stress has been reached. It is 500. So after this point, what you will do, if you remove the load also, then you can see some amount of deformation is occurring in the steel, because we know that it is a ductile material. So beyond this point, you can see if you remove the load also, you can see some amount of deformation is there. But at this point, when the stress is maximum, so corresponding to this point, if you have to find out the stress, then you have, what you have to do, we have to use this formula. Okay, and this formula is coming, and this value you will get from the design curve, not the characteristic curve. Design curve means you have to divide the value by 1.15. So in that case it will be 0.87 Fy. So since this value will be less than this one, so this curve will be below this curve. Okay, so at this point, corresponding to 0.87 Fy stress, whatever strain you will get here, okay, you can calculate that amount of strain by this formula. This is not the formula, this is actually this is the value. Up to this point your strain was 0.002 and this portion was 0.87 Fy by Es according to this curve. Okay, so if you need to calculate strain at this point, we will add this plus this one plus this one. So the value will come as 0.002 plus 0.87 Fy by Es, and Es means modulus of elasticity of steel, and this value is 2 into 10 to the power 5 megapascal. Okay, so this is the meaning of the last array. Okay, according to this graph also, Es value is given 2 into 10 to the power 5 Newton per millimeter square. This is cold steel deformed bars, means this is our HYSD bars. Okay, you can see here the values are given, and this is our mild steel bar. That means this is our definite yield point, means it is our mild steel bar. That means Fe250. For Fe250, this is the graph for stress strain, and for HYSD bar, this is the graph for stress strain. Okay. Okay, so this is the meaning of the assumptions. So I think all the assumptions are over. Yeah, the maximum strain, yeah, this is the value. The maximum strain in tension reinforcement at the Shaler shall not be less than this one. Fy divided by 1.15 Es, that means 0.87 divided Fy by Es divided plus 0.002. This value. 0.002 plus 0.87 Fy divided by Es. Okay, so I hope all of you have understood whatever we have explained today, and in the next class we will start the numericals. Okay, so I will show you how to solve the numericals, how to use the formulas. Okay, so I hope all of you have understood whatever we have discussed, but all of you please go through it. Okay, in the IS code everything is given, or in the internet also you can search it. Okay, but at the end of the numericals only I will share the PDF with you, not now. Okay. Okay, but I will share the images with you so that you can go through it. Okay, I will share the images with you just after the class now. Then you go through the images and go through the IS456. Okay, and if you have any doubt, you can ask me always. Okay, you can ask me in the next class, or you can ask me personally also. Okay, thank you everyone for attending the class.